Welcome to Calc Chats 8. Today we're going to be talking about properties of definite integrals. So far we've talked about how the definite integral is also called the area under a curve. We've been able to use geometry using our area formulas. We've been able to use Riemann sums, midpoint, left, right, and trapezoids in order to estimate the areas under curves. And so today we're going to talk about properties of integrals that are going to help us find even more ways to find the area under even more curves. So integrals, they have similar properties to limits and derivatives, and we're going to kind of see how they relate. So our first property here is our zero property. So this just states that if I'm taking the integral from A to A, so from the same points, that area underneath the curve is 0. And if we look at just a simple linear graph, if I'm looking for the area from 2 to 2, I can't really make a rectangle out of that area, so the area is 0. Our additivity property says that if I'm integrating the same function from A to B and then from B to C, it's equal to integrating the function from A to C. So if we look at our first linear function here, and if we say, okay, we're going to integrate it from 1 to 2 and then 2 to 3. So we integrate it from 1 to 2 and then from 2 to 3. We could have just integrated it from 1 to 3, and that would have been the same area. So as long as we're dealing with the same function and our lower and upper bounds are the same, so those b's match up, we can just say it's the integral from A to C. So order of integration, normally we see our bounds A to B. So when they're flipped, such as I'm taking the integral from B to A, that's the equivalent of taking the integral from A to B and making it negative. So that negative sign matters. So whenever I go backwards, so if I were to take the integral from 3 to 2, from 3 to 2, if I go backwards, that area is going to be negative. So that's one of our properties of integration. So our constant multiple property, this says that if I'm integrating a function, so k times a function, that's the same thing as pulling that k out and multiplying it by the integral of that function from A to B. So with this, I can also extend it to negative signs because this is technically -1. So when I integrate negative f of x dx, I can just pull out that -1 and just integrate f of x, and then multiply that integral by -1. And that's going to get me the same area. So sum and difference, when we integrate on the same bounds f of x plus or minus g of x, it's the same thing as splitting up those integrals. So there should be a minus down here as well. So as long as I have the same bounds, so normally we might start on this section and work backwards. If I'm given two functions that I'm integrating on the same bounds, I can just combine them into one integral as long as they have the same bounds A and B. So here's some basic examples of things that we might see when using these properties. So this first one is I'm integrating from 1 to -1 f of x dx. And so my integral from -1 to 1 of f of x dx is 5. So when I flip my bounds, remember, I put that negative sign. So that becomes -5. Here I'm integrating from -1 to 1 f of x minus h of x dx. So I look and I see that both f of x and h of x, their integrals have the same bounds. So I can just take 5 minus 7 and get -2. So that's our sum and difference property. And then this last one is going to be our constant property. So I see I am integrating 3 times f of x. So I can pull that out. And this integral is 5, so I'm just going to take 3 times 5, and that's 15. So now we're going to talk about how to take the average value of functions. So when we think about the average, we think about taking the sum of the numbers and dividing it by the number of numbers. And that is going to get us our mean. When we take the average value of a function, we want to find the average value across a certain interval. So the average y value across an interval. So that's our goal with the average value of a function. So we can use integrals to help us with this. So here we're given the equation y equals x, and I'm looking at it from 1 to 3. And so if I think of the integral, if I think of very tiny rectangles, I'm summing up all of my y values. So I'm summing up all of these y values. And I'm taking it over the interval from 3 to 1. So I can say that my integral is my sum of numbers. And in order to find the average, I need a number of numbers. So for this, we use our interval for. So our interval is our number of numbers. So when I take the average value of a function, I take the integral of that function, so I find the area underneath the curve, and I divide that by our interval. So I divide that by 3 minus 1. So we're going to kind of put this into more concrete notation. So the sum of my numbers, we said, was our integral. And then our number of numbers, this is where we take our upper bound minus our lower bound. And so we can rewrite this as 1 over 3 minus 1 times the integral from 1 to 3 x dx. And so this idea we're going to use to find the average value of our functions, and I'm just going to rewrite it using kind of dummy variables. 1 over b minus a times the integral from a to b of f of x dx. And so this is how we use the integral to help us find the average y value across our function. So now extending this leads into the mean value theorem of definite integrals. So mean value, we can think as the average value of a function. So our mean value states if f is continuous, on AB, a closed interval AB, then at some point C on the interval AB, we can say that f of C is equal to 1 over b minus a times the integral from a to b of f of x dx. So all this is saying is that it guarantees that our average value is on that interval. So let's see how the mean value theorem plays out using the function y equals x on the interval 1 to 3. So we're trying to find the average value. We're trying to see if the mean value theorem actually works. So I'm given this function. So first thing I want to do is I want to find the integral from 1 to 3 of x dx. And I see that this is a trapezoid, so I'm just going to use a single trapezoid. So this base is 1, this base is 3. If we plug in our y values, we get 1 and 3. And then this is 2, because 3 minus 1 is 2. So my area for a trapezoid is 1/2 times 1 plus 3 times 2, and that just ends up being 4. So in order to find the average value then, that's the total area. In order to find the average value, I want to take 1 over 3 minus 1 times 4. So here I get 1/2 times 4, and I get 2. And so if I look up at my curve, at x equals 2, that y value is also 2. So the mean value theorem just guarantees that the average value of our function is on our graph within that interval. So we're going to kind of explore this more in class. So please come to class with any questions that you may have, and like and subscribe. Thanks for watching.